Take everything out of a room, the furniture, the air, every single molecule of gas, every speck of dust, every particle of any kind. Pump it all out until you have created a perfect vacuum and ask yourself what is left, and your intuition will say nothing. Empty space, avoid a complete absence of anything at all, and that intuition turns out to be one of the most spectacularly wrong conclusions in the history of human thinking, because modern physics has discovered that what we call empty space is actually one of the most violent, energetic, and structured things in the entire universe, seething with activity at scales so small we cannot directly observe them, constantly creating and destroying particles out of what appears to be pure nothingness, filled with fields that stretch across the entire cosmos and never truly switch off. And understanding what nothing actually is, or more precisely why nothing cannot exist, is one of the deepest and most unsettling journeys physics has ever taken, touching on quantum mechanics, general relativity, particle physics, cosmology, and some of the biggest unsolved mysteries science has ever faced. Let us start with the classical picture, the one that felt obvious for most of human history, because for thousands of years, philosophers and scientists debated whether a true void could exist at all. And the ancient Greeks were divided on this. Aristotle famously declared that nature abhors a vacuum, that empty space was a logical impossibility, and that any void that formed would immediately be filled by surrounding matter rushing in, while the atomists like Democritus argued the opposite. That the void was real and necessary, that atoms needed empty space to move through, and this debate went unresolved for centuries until the 17th century, when Evangelista Torricelli created the first laboratory vacuum by inverting a tube of mercury into a dish. And the space that appeared at the top of the tube was initially celebrated as proof that the void was real and achievable. But even then, as soon as physics got sophisticated enough to actually probe what was happening in that space, it became clear that something was going on in there that no one had anticipated. The first hint that empty space was not truly empty came from one of the strangest predictions of quantum mechanics, a prediction so bizarre that even the physicists who made it struggled to accept it. And it comes from a principle you may have heard of called the Heisenberg uncertainty principle, which most people know as the idea that you cannot simultaneously know the exact position and exact momentum of a particle. The more precisely you know one, the less precisely you can know the other. And this is not a limitation of our measuring instruments. It is a fundamental feature of reality built into the fabric of the universe. But what most people do not know is that the uncertainty principle applies not just to particles, but to fields. And specifically, it means that the energy of a quantum field at any point in space can never be precisely zero. Because if the energy were exactly zero, that would mean we knew its value with perfect precision, and the uncertainty principle forbids that. Which means even in a perfect vacuum, even in the most empty region of space imaginable, quantum fields are always fluctuating, always jittering, always carrying some non-zero energy. And these fluctuations are called quantum vacuum fluctuations. And they have real measurable physical consequences that we can test in the laboratory right now. The most famous consequence is something called the Casimir effect, first predicted by the Dutch physicist Hendrik Casimir in 1948 and experimentally confirmed with high precision since then. And the setup is almost absurdly simple. Take two perfectly flat uncharged metal plates and place them incredibly close together in a vacuum separated by a distance of just a few nanometers, and what happens is the two plates are pushed together by a measurable force. A real physical force that you can detect even though there is nothing between them, no air, no charge, no particles of any kind. And the reason this happens is that the quantum vacuum fluctuations between the plates are restricted. Only fluctuations whose wavelengths fit neatly between the plates can exist in that gap, while outside the plates all wavelengths are allowed. And this asymmetry in the vacuum energy on either side of the plates creates a pressure difference that pushes the plates together, proving beyond any doubt that the vacuum is not empty, but is instead filled with real physically consequential energy that can push things around. But quantum fluctuations are only the beginning of what is going on in empty space, because vacuum fluctuations are not just abstract energy jitters. They actually produce real particles. Pairs of particles that pop into existence out of the vacuum for an incredibly brief moment, and then annihilate each other and disappear, and these are called virtual particles. And the word virtual is important because these particles do not persist the way real particles do. They borrow energy from the uncertainty principle, exist for a time inversely proportional to the amount of energy they borrow, and then return that energy when they annihilate. All within the window allowed by quantum uncertainty, and under ordinary circumstances these virtual particle pairs, an electron and its antiparticle, the positron, or a quark and an antiquark or any other particle-antiparticle combination, appear and disappear so quickly that they leave no trace. But near a black hole something extraordinary happens, something Stephen Hawking predicted in 1974, which is that when a virtual particle pair appears right at the boundary of a black hole called the event horizon. One particle can fall inside the black hole while the other escapes into space before they have a chance to annihilate, and the escaping particle becomes real. It carries away real energy. And since energy must be conserved, that energy has to come from somewhere. And it comes from the black hole itself, meaning the black hole slowly loses mass over astronomically long timescales through this process, radiating away energy, as what is now called Hawking radiation. And this means that the vacuum fluctuations of empty space are not just a laboratory curiosity, they are slowly inexorably evaporating every black hole in the universe. Now we need to go deeper. Because vacuum fluctuations and virtual particles are a consequence of something more fundamental, the quantum fields that permeate all of space, and to understand this, we need to understand what a quantum field actually is, because in the framework of quantum field theory, which is the most accurate description of fundamental physics, ever developed particles are not the fundamental things in the universe. Fields are, and a quantum field is a mathematical object that has a value at every single point in space and time simultaneously, stretching across the entire universe with no gaps, and what we call particles are actually excitations of these fields, ripples or disturbances in the underlying field, like waves on the surface of an ocean, and the ocean is always there even when there are no waves. And in the quantum vacuum, the ocean is never perfectly still, it is always rippling at the smallest scales, and the standard model of particle physics describes 17 fundamental fields that fill all of space: the electron field, the quark fields, the photon field, which is the electromagnetic field, the Higgs field, and others. And every point in what we think of as empty space is actually a superposition of all of these fields existing simultaneously, all fluctuating, all interacting with each other. And the vacuum is therefore not an absence of things, but a specific state of all these fields simultaneously. What physicists call the ground state, the lowest possible energy state, and crucially that lowest energy state is not zero, it is a specific non-zero value called the zero-point energy. And the total zero-point energy of all the quantum fields filling the observable universe is what physicists call the vacuum energy. And this is where one of the biggest unsolved problems in all of physics lies. The vacuum energy should be enormous when you calculate the contribution of quantum fluctuations to the energy density of the vacuum. The theoretical prediction comes out to be somewhere between 10 to the power of 60 and 10 to the power of 120 times larger than the value we actually observe when we measure the energy density of space. And this mismatch, a factor of 10 to the 120, is the largest discrepancy between a theoretical prediction and an experimental measurement in the history of science, so large that physicists call it the worst prediction in physics. And it goes by the name of the cosmological constant problem, and nobody knows how to solve it. Nobody understands why the vacuum energy we calculate from quantum field theory is so catastrophically different from the one we observe. And this is not a minor technical puzzle. It is a fundamental crisis at the heart of our understanding of physics, sitting right at the boundary between quantum mechanics and general relativity, where the two great theories of the 20th century refuse to be reconciled. And what is the vacuum energy that we actually observe in the universe, the real measured value? It is what cosmologists call dark energy, the mysterious component that makes up roughly 68% of the total energy content of the universe and is driving the accelerating expansion of the cosmos. Discovered in 1998 when two independent teams of astronomers measuring the brightness of distant supernovae found to their complete shock that the universe was not just expanding, but expanding faster and faster over time. And the only way to explain this acceleration within general relativity is to include a term in Einstein's equations representing an energy density of empty space itself, a repulsive contribution that pushes the universe apart at every point simultaneously, and we call this the cosmological constant, denoted by the Greek letter lambda, and it appears to be incredibly small, tiny enough that it has no detectable effect on local physics, on atoms, on solar systems, on galaxies, but because it fills every cubic centimeter of the vast expanse of space. Its cumulative effect on the large-scale structure of the universe is dominant and growing, and in the far future, as the universe expands, the density of matter and radiation will dilute away while the vacuum energy stays constant. And eventually, in hundreds of billions of years, the expansion will be so fast that galaxies outside our local group will be receding faster than light, unreachable forever, and ultimately the universe will approach what cosmologists call a de Sitter space, cold dark, emptied of all structure except the residual warmth of the vacuum itself. There is one more layer of strangeness in the physics of empty space that we have not yet touched, and it is in some ways the strangest of all, and it concerns a concept called the Higgs field, which is one of the quantum fields filling all of space, but unlike the others plays a completely unique role. The Higgs field is what gives most fundamental particles their mass, and it does so by having a non-zero value in the vacuum. What physicists call a non-zero vacuum expectation value, meaning that even in perfectly empty space, the Higgs field is not at zero. It has a specific value everywhere in the universe simultaneously. And particles moving through space interact with this pervasive background Higgs field, and that interaction is what we experience as their mass. So mass itself is not an intrinsic property of particles, but rather a consequence of how strongly each type of particle couples to the Higgs field that fills what we thought was empty space, and without the Higgs field. Electrons and quarks would be massless and would travel at the speed of light, and atoms could not form and chemistry would not exist, and neither would we. So the non-emptiness of empty space, specifically, the vacuum expectation value of the Higgs field, is the reason that matter is the way it is, the reason that structure can exist at all in the universe. There is also a deeply disturbing possibility that sits in the background of all this Higgs field physics called vacuum decay or vacuum metastability. And it goes like this. The current value of the Higgs field in our vacuum represents what appears to be the ground state. But calculations based on the measured mass of the Higgs boson discovered at CERN in 2012 suggest that our vacuum might not be the true lowest energy state. It might be what physicists call a metastable state. Like a ball sitting in a small valley on the side of a mountain, rather than at the very bottom, stable enough to persist for enormous timescales, but not perfectly stable. And if this is true, then somewhere in the universe at some random point, a quantum fluctuation could trigger a transition to the true ground state, a lower energy vacuum, and this transition would propagate outward from that point at exactly the speed of light as an expanding bubble of true vacuum. And inside that bubble, the laws of physics, the masses of particles, the strengths of forces, the structure of chemistry, would be completely different. And the bubble wall, as it expands, would destroy everything it encounters with no warning because it travels at light speed, and we would never see it coming, and this possibility is called vacuum decay, and it represents perhaps the most final ending imaginable, not a bang. Not a freeze, but a silent rewrite of the laws of physics spreading outward at the speed of light until the entire universe is transformed into something utterly alien and unrecognizable. So the next time you look at what seems like empty space, the gap between atoms, the void between planets, the vast expanses between galaxies, remember that none of it is empty, not even close, that what you are looking at is a seething, fluctuating, field-filled, energy-carrying, particle-generating, universe-expanding, mass-giving structure that we call the vacuum. And the fact that we gave it a name that means emptiness is perhaps the greatest irony in the history of science, because the vacuum is not nothing. It is the most fundamental something that exists. It is the ground state of reality itself, and everything, every particle, every force, every structure, every experience exists not in spite of it but because of it.